okay? Okay, sure. And another thing that I wanted to ask is while speaker is setting up is that many of you actually ask about discussion groups. And you probably notice we are finishing almost always around 2, or we have something else. So if there is a discussion group that you're interested in particular that you would like to lead or that you would like to talk to, I mean, look where we are. We are here. So just talk to the people. There is this break, like, I mean, we are officially here in the Institute. Exactly. So that's what you can do. I mean, after the talks, if you have some good ideas that you would like to discuss, just come here, say, can I have a mic for a second? Explain what you would like to have discussion group on. And that's it. So, like, let's kind of try to be, like, as productive as possible, but also like, let's kind of not go with the too many official structure because, like, no need to sign up, no need to kind of, let's kind of do some research what's good. Okay. Nancy, your talk.
Okay, thanks, Rutsika and Moshe for the invitation. So I am not a program synthesis person, so disclaimers first. I am not a computer scientist either. I am a control theorist by training, but I have been using formal methods, and this title is slightly different than my original title, because listening the talk and seeing the audience, I thought this might be something you are more interested in. But at the end, I will do something like choose your adventure point. Then I can talk about one thing, or I can talk about live things as abstractions. Life as an abstraction. Okay, so I am a control theorist, and I work with hybrid systems and cyber physical systems. And we have seen lots of theoretical advancements here. I will try to show you how to make them work in real world. And this is going to be my view of several formal methods techniques. And it might be different than a computer scientist's take on it. But I think this will inspire some discussion. OK, so for me, the biggest problem in formal methods is verification. And in my world, verification problems are like this. You are given a plant, which is the thing that you are trying to control. For example, it's your robot, it's your autonomous vehicle with a model. And you are given a decision-making software that reads information from the sensors of this plant and that decides on the variables that goes into the actuator so that your machine moves. And what we want from verification is that you get this white box system, plant plus software, and you get a specification, and you want to come up with a correctness proof or a counterexample. This is great if you can do it, because it gives you very strong guarantees. But in my world, this is very hard. For hybrid systems, verification is typically undecidable. And one thing, one observation people in control systems made is that usually most of the complexity in this problem, even though you are just developing sound but incomplete methods, comes from the autonomy software. So most of the complication comes from the autonomy software because you understand your plant fairly well. For example, if you are trying to control autonomous vehicles, you can go to any mechanical engineering department and find a course on vehicle dynamics. We teach people how to do these models. And we have different types of models, very complicated models, more reduced order that are more useful for control design. So this, however, the software part coming from computer science, that's giving us some trouble because when you have millions of lines of code, this is hard to model. You cannot directly use your C or Python code. You need to model it somehow to be consistent with verification tools. And it's also hard to scale if this is very complex. So what are some alternatives to verification? One thing this community does is synthesis. So in synthesis, instead of this complete model, we get rid of the part that's complex, And we start with a partial white box system. So we have a plant. And the question we ask is, does there exist a software so that when we close the loop around the software, I can satisfy the specification? So this is, again, very similar to program synthesis. Maybe the difference is that we have this, we differentiate between environment from the plant. So plant is a special object for us. And this is also done this way in discrete event systems that's closer to synthesis. And if you have a good synthesis method, you either get a software with correctness guarantees and a winning set, validity domain. Or you can get a proof of impossibility. And again, if you are working with hybrid systems, verification is even harder than synthesis. Synthesis is even harder than verification. If you can do this, you get strong guarantees. It avoids the complexity induced by software, but maybe we are cheating a little bit here. We are pushing the complexity from the input to the output, because now if we really want to do something complex, the synthesis algorithm should generate that complex software. But one thing I really like about synthesis is it explains some fundamental limits. And I think this is particularly useful as a design tool, even though you don't want to use the software that's generated. These impossibility results are quite useful. For example, if you get an impossibility result, then what you know is that maybe you are asking too much from your system. You can relax your specification a little bit. Or maybe your system is not powerful enough. You can add better actuators, better sensors, and go from there. So disadvantages, as I said, this is harder than verification. And in my world, this typically works with more limited specifications. Although in theory, it works with whatever you can do with verification. This is at least the things that we can work in practice with continuous domains. It's more limited. And specification correctness and completeness is more crucial in this domain, because if you are doing verification, you think about one specification, you verify it, you think about another specification, you verify it, and you can do something somewhat compositional. But if you are doing synthesis, you cannot do, oh, I synthesized for property A, now I synthesized for property B. You cannot guarantee that there exists a single software that satisfies both. So you should really think about your specification carefully. And in one of the adventure lines, I will talk a little bit about this further. And one of the problems here is that there are almost no synthesis approaches for perception or learning components. So we have some verification in these domains, but maybe not that much synthesis. So I worked on synthesis a lot, and we try to make this happen with real systems. And one of the applications I worked on was autonomous driving. This was almost 10 years ago. And we looked into like very simple, at the time they weren't that simple, but we looked at simple functionality like adaptive cruise control and lane keeping. And it works. So we have this test facility at Michigan. This vehicle is driven by a software that is totally synthesized. We did code generation as well. So you give your specification, you give your vehicle model, you click a button, it synthesized code, and we put it there. It does fairly well with the simple functionality. We weren't quite sure initially, so we have something like a digital twin. So we tested in simulation as well. But it kind of works. So what did we learn from doing synthesis in the real world for physical systems? So one thing we learned is putting correct and automatically synthesized software on a car is feasible. So all the work you are doing in this room, it's very useful, and we can use them in real machines. It doesn't mean that things will work. So there are failure cases, but having formal specifications and formal models were quite useful in understanding root causes of failure. So we could use these models that we use for synthesis and specifications as monitors, and we can just take the logs of failed experiments, look at the log, and look at where our model assumptions failed. For example, one thing we realized is that we weren't modeling any actuator delays, but apparently the command that you give to a steering wheel, and by the time your actual tires rotate, there's a delay there that affects your dynamics. And it wasn't in our original model, but looking at the logs, we realized this was one of the problems. So the other thing that we realized is we can do this, but we are being a little conservative. For example, most of the synthesis methods, they use the current state. But if you think about driving a vehicle, looking at the current state is more or less like digging a hole underneath your car, looking like this, and trying to drive that way. But we have lots of sensors and things that give you information about the future. And there are also methods in synthesis that uses this foresight or preview. So this motivated lots of future work where we try to synthesize safety controllers with learned models, with delays, with predictions, where we use some ideas from this community, but we also used a lot the vector space structures in the dynamic models that we have. I am going to show you one result, for example, for delays, how this model structure can help. And in general, if you are just working with arbitrary transition systems, you don't have that vector space structure. You don't have that much algebraic structure. Or maybe you do, and you tell me how to utilize that. OK, so here is a more specific problem, maybe more familiar for people with a background in control. But the ideas are very similar for discrete modeling as well. So here is my system model. X is state here. T plus 1 is state in the next time step. Is a function of current state, a linear function of current state, a linear function of the input tau d steps back. So this is modeling the delay. Typically, what you would see is that you won't have this tau d here in models. And that was our original model. But in general, you will have tau d here. And D here is the adversary. So in the game setting, U is what we are controlling. D is what the environment controls. And we have some budget for U. So U lives in a compact set. And we give some budget to the disturbance as well. D lives in a compact set. So in the car example, this is just the distance between two vehicles. For example, if I am doing adaptive cruise control, my speed, the other car's speed, U is my acceleration inputs, and D is the acceleration inputs of the other car. So I can take this model. This doesn't have the nice Markovian structure, but I can embed it in a higher dimensional model where I recover the Markovian structure. And this higher dimensional model will look like this. This is essentially embedding the state with a history of inputs and one-step delays, such that in this model, the thing that I control is this U, but this U is affecting the state after going through this tau d step delay. And if I want to solve an invariance or safety game on this thing, I can pose the same problem here. So if I want X to be in some safe set S for all times with some input budget capital U, I can equivalently say, oh, I want to find a safe set for this Markovian model. I want to find a controller that renders this Markovian model safe, where my safe set is defined as my original safe set that's on the actual state times U to the tau. This is where my input has to live. So this way, I can take this non-Markovian problem and convert it to a Markovian problem. And here we are trying to find a maximal invariant or maximal controlled invariant. So you can imagine this is the winning set of a safety game. in a sense. So what is the problem here?
Given to you, you have to come up with it.
A and B are given. For in this setting, yeah, yeah. So one problem is if tau d is large, this is a very large state space. The question is, I already said these problems in continuous domains are hard. They scale, even the sound but incomplete algorithms scale typically exponentially with the dimension of the state space. Now I am increasing my state space much further. But one thing, for example, we showed using the structure here, we can do some reduction. And this is maybe a complicated slide, but I can define a mapping T from this large state space to a state space that's still x-dimensional. So this is a linear mapping of this large state space to a smaller state space that's independent of the dimension tau d. And I can write down the dynamics of this object that I call x hat. And this object has this nice dynamics. And I can do my synthesis in this auxiliary space. And one thing we can show is that if you do this reduction, if you synthesize here, you can lift it back. And whatever invariant you synthesize here, with this lifting function, gives you an invariant here. So you can think maybe this is a simple simulation type property. What is interesting here is that this reduction is lossless in the sense that if I do a maximal invariant for this low dimensional system, and if I do this specific lifting, I get a maximal invariant in my high dimensional system as well. And this is using the vector space structure in a smart way to come up with this exactness result. And how does it work in practice? For example, if I go and try to do my synthesis over here, this is an exponential, this is a log plot. So this is how things scale. And if I do my synthesis in this lower dimensional space and lift, this is how the things scale. It's still increasing a little bit because this inverse mapping is a little complicated if your dimension is increasing. Okay, so this is one example of using this state space structure to do things efficiently. So this was for synthesis. Another alternative to verification is falsification that's used a lot in hybrid systems and cyber physical systems. Here, instead of a white box model, you work with a black box system. You have your plant and software in a box, you can query that. And you still have a specification, you try to search for counterexamples. And typically, if you cannot find anything, you cannot say too much, unless you use some statistical arguments, but I won't go into that. So the nice thing here is that you can handle arbitrarily complex models, including learning-based components, and there are industry-adapted tools. So this is used actively in industry. Sanjit was involved in some of these tools, tool development as well. So the disadvantages here is that the conclusions are weaker. And one of the things that I didn't like much about falsification is that there is no explanation of counterexamples. Sometimes it can give you trivial counterexamples, and you never know if the counterexample is due to an error in your, or a limitation of your hardware, or it's really a software bug. And being able to differentiate those two it's a powerful thing. So we looked at this, and we came up with this another alternative that I call synthesis guided falsification. As I said, in falsification, you work with this black box that contains both the plant and the software. So this is system under test. But in my world, most of the time, we really have good models for the plant. The difficult part itself is the software. So there's some partial knowledge of the plant. And our idea was, can we use this partial knowledge and do some synthesis? If you will, we are synthesizing things like shields. And can we use that object to do this search a little bit more carefully? And it turns out that you can do this. And we applied this, for example, in autonomous driving settings. So we have our car models, Comma AI. Have you heard about Comma AI? So it's kind of an interesting story. This is a startup that claimed that given almost any car model that can give you a small hardware with a camera that you can put on your windshield, and that will turn your car into something equivalent of Tesla Autopilot. And they wanted to sell this thing, and NHTSA was like, no, 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 you cannot, it's not safe, you cannot sell it. Then the founder of the startup said, okay, if you are not letting me sell it, I will just make everything open source. So the code is on GitHub. The hardware is open source as well. So if you're interested, you can just download the thing. You can build 3D print this parts of this hardware, put it on your windshield, and they tell you how to hack into your canvas, and you can make your car equivalent to a Tesla. So we took this and we did our falsification analysis. For adaptive cruise control, we couldn't find any errors, in the sense that we couldn't make it crash. But one thing we found is that they have the safe distance coded in their commands. It was saying, oh, don't get closer than 3 meters to the front car. And they were violating the safe distance they set themselves, but it wasn't crashing at all. For lane keeping, we could find lots of scenarios where you can make this steer out of the lane, although there exists another action or another controller that will keep you in the lane. We also extended this to vision-based systems, where here I have a neural network controlling the vehicle, taking the image and deciding on the actuation. And if you randomly generate trajectories, this neural network is trying to get around this car. And for random sampling, it always gets around the car. Now, using similar ideas, we can manipulate this image a little bit, and we can do these type of things. So this is same controller, slightly manipulated image, and we can get it to crash. So I am already running out of time. So this is kind of my view of formal methods for CPS. So things that I didn't talk about is there's a big elephant in the room here. That's the specification. So we did lots of work on understanding and learning specifications. And to give you maybe a teaser, wait, where's my, this is the wrong slide. How we map these models to your world, we start with these type of models, and sometimes we create discrete abstractions so that we can directly use synthesis methods. Sometimes we took the algorithms from synthesis world. You have fixed point algorithms, and we try to apply and compute those fixed points on the continuous domain. And sometimes we do this incremental abstraction refinement. We start with a discrete abstraction. If we cannot solve the problem, we go back to the continuous domain and ask where should we refine the abstraction so that we can get a controller. So I already ran out of time. I will just stop here. But one thing we are now doing is, instead of abstracting into a discrete thing, we can take this object and lift it to a higher dimensional space where we have more structure. For example, if these dynamics are nonlinear, if I lift to a space where I recover linearity, I can do some interesting things. And that was my original talk, but I won't give it. But I am happy to talk offline.
Questions?
So a couple of years ago, I did a seminar at Rice where we read a dissertation on formal methods for AVs.
Mm-hmm.
And at the end of the seminar, I asked the students to vote whether they would be willing to step into an AV. And they all voted no. And the reason was because you have to model the environment. And they all said the model of the environment are unrealistic. Okay, the problem is, yeah, 99% of the time it's predictable. But then suddenly a ball rolls on the road. And we know if there's a ball rolling on the road, there's going to be a child running after the ball. And other than to say a ball is not a threat, so we'll just drive on. So the conclusion was that it's in modeling a realistic environment where the challenge is. Would you comment on that?
So I totally agree. So the examples that I picked, they were mostly highway driving, where it's more controlled environment.
Yeah.
But that's a very good point. How do you model this thing? This model is typically incomplete. If you are like, there are too many things in the world that you cannot think about. And we need techniques that can maybe at runtime understand this model is insufficient at this point and try to augment the model and resynthesize. But maybe it goes a little bit to monitoring, but that's a fair point. But the other thing is, what I would say is, even with simple models, you can get lots of insights into what is possible and what is not possible. And I think that's a useful insight. So the way I think about synthesis is not really, I will press the button and put it in my car. I will press the button and learn something about the system from what comes out of the synthesis.
Would you ride in an AV?
If you go to San Francisco, you can do it right now. They're all autonomous.
I said, I know. I asked, would you? I know she could. I know she could.
If you give me the software and if I can run my test on the software, maybe.
Okay.
Okay. Are there more questions? Can you please pass?
Since we are, you're starting from the continuous models. So let's suppose that you have a model. In your practice, in your expert opinion, what are the continuous results that we are most urgently missing right now for the continuous systems?
So there are multiple challenges on continuous models. For example, if I want to use fixed point type algorithms, the type of things that are interesting is that, for example, in discrete world, you have very efficient techniques for representing sets. It's not clear what type of sets that I should use in the continuous world. So we typically use polytopes, but polytope as an object, when you start doing fixed point, it doesn't have fixed complexity. So every iteration, the complexity of the set that I am computing changes. So what type of set I think that there's some need for understanding what type of set representations are useful, whether those set representations are closed in the type of fixed point operations that you want to do. I think that's one interesting point there. I would say that's one of the interesting things that comes to my mind.
Thank you. Are there more questions? If not, in order to time, let's thank speaker and our once more. And Ras will be the next to set up. So.